All right, so last class, you guys had just the recording for the 3 o'clock one, unless you showed up for the 9. I did see more people there for the 9, so maybe some of you showed up for that one. In that, we went through the ideal Rankine cycle example, okay, and started the regenerative, which we'll continue today. So the ideal Rankine, we have the pump, boiler, turbine, condenser. This is changing phase. We were given isotropic efficiencies, some temperatures and pressures. We need quality, so state information at the turbine exit, thermal efficiency, mass flow to steam. So we set up the TS diagram. You know, we have our pump with our isentropic efficiency, boiler, turbine with its isentropic efficiency, and condenser, right? We have the vapor dome because we're changing phase, okay? We set up a nice table for our properties because there's a lot more properties to deal with in the Rankine cycle, so it's nice to utilize the table to see what's going on, right? We did for the turbine, use the isentropic efficiency to get actual thermal efficiency, set up the equation, did our COEs, use the isentropic efficiency of a pump to get the outlet enthalpy, and mass flow rate of steam. We used the net power output that they gave us with the work net out, and related those to get the mass flow rate of steam that was asked for. Okay, and the regeneratives were, it's 10-53, we're given, it's an ideal regenerative Rankine. They gave us the pressure at the inlet to the turbine, the temperature at the inlet to the turbine, the pressure at the condenser. Okay, they gave us the first pressure, that's for the first extracted steam's pressure. Okay, so that would be right here. Okay, so draw for me here. So right here. Okay, is our first one, and then our second is here, right? And then this is our condenser pressure, right? So we have all kind of the pressures around the turbine, right? 8, 9, 10, and 11 given to us. Then they give us these last two things. We have this temperature leaving the closed water heater is equal to the saturated temperature of the extracted steam. So this is talking about state 6 for the temperature out of the closed feed water heater. Oh, no, sorry. State 5. And then the saturated temperature of the extracted steam is talking about 6 or 9, you can say. Okay. And then here we have the quality out of the extracted closed water feeder is 0 quality. So this one's all talking about 6 also, okay, that we have 0, okay, quality. All right, so then the problem, we're looking for the mass flow rate of steam for the boiler, and they give us a net power output, okay, and a thermal efficiency. We did our TS diagram, okay, so we have, move this over, we have our low pressure, so this is the condenser pressure of the 10 kPa. Yeah. Okay, so we have our 10 kPa. This is 10,000 kPa. And we had, I think, 1,200 kPa. And 600 kPa. So it's our 4 pressures, right? Oh gosh, what did I just do? Sorry about that. Leave it there. All right. We can walk through our diagram. Okay, we had from our schematic, we're starting, we have pump 1. All right, the state 1 goes through the pump 1. Isentropically, we get to 2, right? We have all at 2, 7, 10, and 3 are all at the same pressure because it's open feed water openly mixing. But 7, 2, and 10 are going into the open feed water heater, and 3 is going out. So 10, 2, and 7 are all mixing and providing us with 3. So everything's going into 3. So we get it 3. And again, the inlet to the pump 1 and 3 have a quality of 0, right? And we see that down here. Okay, so you have that quality of 0. All right, so we go through the second pump to 4, so isentropic pump to 4, and then we go through our closed feed water heater from 4 to 5, same pressure, and we get up to the saturation temperature 6. Okay, now we add our heat in the boiler. Okay, all the way to 8, because we're adding in heat, so we're adding entropy, so we go all the way to 8, and 8 takes us to the turbine. So we can expand isentropically. It's an isentropic turbine. We don't have any isentropic efficiencies. All the way through the turbine, 8, 9, 10, 11, and we have constant entropy. We go all the way 8, 9, 10, 11. We get down to that condenser pressure. That's at that vacuum pressure, right? It's only 10 kPa. And then we go and we have our condenser. So we reject heat out. Okay. So we had our turbine, which is our work out. We have our pumps, all right, which is a work in, and then the other pump is a work in, okay. All right, some of the other processes, so we'll start with the lowest pressures extracted stream. Let's go with that one, that's fine. If we do 10, right, 10, we're extracting there 10, which we said is right, we have our point at 10, and we're just going into the open feed water heater and mixing with 2, 7 to get us 3. So 10, basically mixing with 7 and 2 to give us that 0.3 right there. Okay. Now if we go to the first extracted stream, so the higher pressure, we go through. We have a closed feed water here, so 9 and 6 are the same pressure. Okay, so it's a connected pipe. And then we have our valve, which is isenthalpic or constant enthalpy from 6 to 7. Okay, so we're dropping pressure to put it into the open feed water heater. Otherwise, we would have had to raise pressure to put it into the boiler with a pump. Okay, so we drop pressure. We have a constant enthalpy line, isenthalpic to 7. Okay, so 9 takes us to 6 because they gave us that the 6 was a quality. Quality of 0 was given, and then a constant enthalpy to 7, and then that mixes with 10 and 2 to give us 3. Okay. And then we created this amazing table. All right, it's empty, but we can start filling in some of the, grab my page here. Some of the givens, right? I'll start with what was given in the problem, okay, and we'll go from there. Okay, so we have, they gave us all the pressures and they gave us inlet temperature. They gave us all the pressures for the turbine and the inlet temperature for the turbine. So we got, that's state 8, right on our schematic, is the inlet to the turbine. So we have a 600 degrees Celsius, we have 10,000 kPa. They gave us the extracted steam pressures, so that would be 1200, and then 600, and then the condenser pressure of 10. Okay. And then, what else did they give us? I'm going to star this so we can remember that was the givens. No problem. The other thing they gave us was the quality exiting the closed feed water heater, right? So that's state 6. So they gave us that. Okay. So let's see if we can utilize some of this information to fill in some of the rest of the table. Okay, so is there, based upon what we have here and our TS diagram and our schematic, what else can we fill in? Any other values?
8, 9, and 10 are all ones because they're superheated.
They are superheated, so they don't have a quality if you're superheated. 8, 9, and 10. So there's no quality when you're superheated. NA. Okay.
4, 5, 6, and 9 are all the same pressure.
Okay, so 4, 5, 6, and 9, right? So 4, 5, and 8. I mean, so not 6 and 9. Okay, so this is our pressure line, right? So 4, 5, and 8. Let's go here. 4, 5, and 8, same pressure, right? Pump changes the pressure. And this is a closed feed water heater through here. So these are, this line goes and connects directly to that, and 4 connects directly to 5. So the fluids are never touching. Okay, it's just the tubes. Okay. So we have 4, 5, and 8. Okay. You said, let's do that one. 4 and 5 are 10,000 then. And we have 8. All right, we're using that. What else? Anything else?
6 and 9 have the same pressure.
6
10,
and
7,
9.
and 2.
Yep. All right, 6 and 9. 12. And then 10, 7, and 2, you said. And also 3, right? Goes in 10, 7, 3, and 2 are on the same one. What about 1? Which pressure does it have? The same as?
11.
11. Okay, so we got 10. All right, so we have pressures. Okay, so those are the easy ones to fill in. So now we know we have 2 independent intensive properties for 8 because it's superheated. We have 2 independent intensive properties for 6, right? So now we can see whether we can get something else. So is there anything else on this diagram that we can fill in that we know?
The states at 1, 3, and 6 are all the same.
So 1, 3, 6. Not the state, just the quality.
That's what I meant.
Yeah. Okay. So 1, 3, and 6 are all a quality of 0, right? Because, and that's only 6 was given in the problem, right? It told us specifically, but 1 and 3, they're inlets to the pump, and it's a Rankine cycle, so we have a quality of 0 there. Okay. All right. So that sets those 2 states. So those are independent and two independent intensive properties, so we could get anything else that we would potentially need if we wanted to, or when we need it. Okay. What do we know about the turbine? From the properties or the process through there? Is there anything being held constant as we go through the turbine?
The entropy.
Yes, this is isentropic turbine, and it's water, so we can get the entropy directly. Right, so we can know that the entropy is held constant. So we go here, here to here to here is all isentropic. It's messing me up here. All right. So isentropic. All right, and since it's isentropic process between those, we know in this problem we know state 6, but if we knew 9 or 10 or 11, we would know the others too. So we know, we know 8, sorry, not 6, we know 8, but if we knew 9, 10, or 11, we would know that the entropy is constant also. So at 8, we know the entropy because we have two independent intensive properties. So we go into the table, and at that pressure and temperature, look up at our entropy, and we get it, right? And it's isentropic, as it said, so then the entropy is the same. So with the entropy being the same value all the way through, we have two independent intensive properties for 9, 10, and 11, okay? So we can get anything we want again, okay? We actually find out that this has a quality of 0.8341, okay? From getting that entropy. Okay, so we have enough, we could get enthalpy for all those. Okay. We could get enthalpy for the other states that we know. Oh, 9181. Okay, so now we have the enthalpies for most of these, right? Let's think about trying to get all the rest of the enthalpies because we have to eventually solve for thermal efficiency, and that's going to require information about every state usually. Okay, so is there any other information that we can fill in when we look at our TS diagram?
1 and 2 is also isentropic.
So 1 to 2 is isentropic, right? So we have 1 to 2 is isentropic, right? And then that means we have 1 to 2. What else is isentropic?
4 to 5.
4 to 5. Okay. 4 to 5 is isentropic, right? It's pump, isentropic pump, isentropic pump. This is turbine down here, right? All right, so then we have left, and we'll use that in a minute. Or no, it wasn't 4 to 5, right? It was 3 to 4, so it was 3 to 4. Sorry.
Oh, yeah.
Yeah. All right. So then we have left is we need stuff about 5 and 7, right? Do we know anything about 6 to 7? What did I mention that kind of process is? The valve or the trap? Or from your last exam?
H is constant?
Yes. Yeah, H is constant, so it's an isenthalpic. When you have a valve, okay? Delta H is the same. Okay, there's no pressure, there's no work crossing our boundary, and there's no heat crossing it. You're neglecting potential energy and you're neglecting kinetic energy. So all you have is the enthalpy with mass flow rate flowing in and the enthalpy with mass flow rate flowing out. The mass flow rate's the same, so those you can divide it out and it goes to 0 on that part. So then you just have enthalpy change. Okay. So it's isenthalpic, enthalpy is constant. So we get to just grab our enthalpy from state 6. We don't even have to go look in the back. Okay. All right. So then 5, and then we'll go into depth on the pumps that was mentioned. So this is pump 1. It's pump 2. All right. So we have something for 5, and this is where we go back to the givens. Okay. And they actually told us some information about 5. The temperature out of the closed feed water heater, so that's state 5, is equal to the saturation temperature that of the extracted seam. So that's saying the Tsat, the saturation temperature at state 6 or 9 is equal to the temperature out at 5. And you can kind of see that here with the temperature being the same from 5 to 6 in how I drew it. So that means we need to get Tsat at 6. So that's the toughest understanding of that problem for this table. We get 187.96, and it's the same at 5. Okay, and then this is a compressed liquid at state 5. So what we end up finding is we approximate for a compressed liquid at the saturation temperature conditions what that enthalpy is. Well, if you look up the enthalpy for a saturated liquid at 187.96, it's the same as we have for state 6, because the saturated liquid at that temperature is this. So we'll end up having the same enthalpy there. Questions so far? All right, let's do the pumps. So pump 1, all right? We said it's an isentropic pump, right? So if we did our isentropic efficiency of the pump for like we did for the last example, you have isentropic pump over actual. But then we also use that V delta P, right? Specific volume, change in pressure for isentropic, because we can use that reversible steady flow. And take the specific volume out of the integral because it's incompressible. Assume it's incompressible. We can't do this for the turbine because the specific volume is changing, right? So but we can do it for the pump. So we do that, take it out, we have V delta P, right? What's the isentropic efficiency of this pump? I would say don't overthink it. If it's an isentropic pump at 1 and 2, right, because we just have an ideal Rankine that didn't give us efficiencies, what does that mean for the isentropic efficiency?
Is it just one?
Yeah, it's just 100. It's 100%, right? So or 1, right? So that means it's 1. That's isentropic. So that means H2 actual and H2S are the same. Okay. So then we have this, right? Well, we have the pressures. We have all our pressures in this problem, P1, P2. We have our enthalpy at state 1. We do need to get the specific volume at state 1, which we can just go grab it from our table. Okay, so now we have that. So that means we can get H2 and then the last thing, so we have H2, the last enthalpy we need is state 4, right? So what do you think we do for that? Same thing, right? So I'm gonna grab, since I'm up here by this table, I'll grab our specific volume. That's 0.001101. There you go. All right, so we do pump 2. And we're just gonna get enthalpy 4 minus enthalpy 3 is V3, P4 minus P3. We have our pressures. We already got our specific volume. We have our enthalpy at state 3. So again, our only unknown is H4. So we can solve for enthalpy at 4. We get 680.73. All right, so we have every enthalpy, so we have state information. So we should be able to get a thermal efficiency and anything else we need for this problem, okay? All right, but that's part B. The first part is the mass flow rate of steam for the boiler for work net out equal to 400 megawatts. Any ideas? At least where to start? We did something very similar, at least in the start of this problem in the last problem.
We need to solve for the work of the pumps and the turbine.
So yeah, the work net, right? So let's write that down first before we start solving. Okay, so let's do, so they're asking for the mass flow to steam through the boiler, right? So I'm going to use mass flow rate 5, which is the same as 8, right? The boiler's inlet is 5, the outlet's 8. Okay. Well, work net out, right? That's where we, for the last problem, where we did this, where we set up the power net out, mass flow to steam, work net out, okay? Load up, here we go. All right, so in this case, so you have work net out because mass flow rate is at 5, okay? And then you have that per unit, per kilogram work, but I'm gonna do it in an extra step. Because it becomes important later on. Okay, so this, right, if we cancel mass flow rate of 5 off, we would just have the power net out equal the power net out, right? But we want it in this lowercase net work, okay? But this net work is based upon dividing it by mass flow rate 5, okay? That's important because if you look at the schematic, the mass flow rate's changing through everything, okay? We don't have the same mass flow rate going through every component, right? We're extracting some mass flow rate out of the turbine, so we're changing the mass flow rate. So it matters that we're dividing by mass flow rate 5 in this case. And the other, like the last example and a lot of the things we did in the last chapter, right? It's only one inlet, one outlet. It's the same mass flow rate flowing through all the devices. So when we make it, and when we divide by that mass flow rate out, like here, when we made it lowercase work net out, it didn't matter as much because all the mass flow rates were the same through going all the components. So we didn't have to be careful, right? Here, we got to be careful with this, okay? And we have 5, okay? All right, so then we have work net out, right? So you said we can do of the pump, or of the work net out, or power, I'm going to start with power, is the turbine. So our turbine work minus the, or power, sorry, pump 1 minus pump 2, okay? But we'd have to divide that by mass flow rate 5. So that would get us okay, but they're all these are based upon mass flow rate 5, right? Because that's what we divided by. How else could we get work net out? What have we done in some of the other problems, this chapter and last chapter? Say we look at the full schematic.
We could do Q in minus Q out, I think.
Right, yeah. So if you did basically your boundary around this whole thing, the whole cycle, the only thing crossing your boundary is your heat in, heat out, and then the works, which you can make it as a work net, right? So you could also do that work net out is Q in minus Q out, right? But we still have to, again, divide by mass flow rate 5. So you get the work net out per mass flow rate 5, right? Q in, Q out, and again, these are all based upon mass flow rate 5, okay? Any questions on that? Okay, so we can go this route of using this equation or this one, right? Okay. They'll both end up having, what you'll see, a lot of the next steps will be similar, except for you just got to, in this one, we got to do one more COE if you do it with the works, right? But they'll both give you the right answer if you go down the process the correct way, okay? So I'm going to do this one, okay? Just because that's what I have numbers on. I'm going to do this, the one with the heat, okay? But you could go the other route and get the same answer eventually, okay? So we'll start with the easy one. We need to get Q in and Q out. We'll start with Q in. What do I do to get Q in?
We would have to look at 5 to 8.
Yeah, so we do our COE of the boiler, right? Okay, it's open system. One inlet, one outlet. Okay, so that's 5 to 8, right? I forgot to put that earlier. 5 to 8. Okay, I'm gonna write the COE. We neglect steady state. No, neglecting kinetic and potential. And I left in the mass flow rate, so I didn't divide out mass flow rate yet, okay? All right, so for the boiler, we don't have any work, right? So we get Q in is mass flow rate 5 H 8 minus H5, okay? Okay, so divided by mass flow rate 5, that's our Qn. We have H8 minus H5. We have our enthalpies. We get 28, 27 kilojoules per kilogram. Okay. All right, so we've knocked that one out of the park. Now we have to get our heat out. Which one's that?
It's the condenser, so 11 to 1.
Yeah, so we got to do our 11 to 1. Okay. Condenser, so it's still open system. 1 inlet, 1 outlet. All right, so we're going to start with that same COE, that steady state. One inlet, 1 outlet, collecting kinetic and potential. All right, again, no work. The inlet is 11. All right, so if we made this Q dot out, that becomes H11 minus H1. Okay, so here's where a little bit of the trickiness comes in. What do you think I have to do next? Do I divide by mass flow rate 11?
No, I guess you divide out by mass flow rate 5.
Yeah, so to make the algebra correct, because we did work net out by 5, so, or the power net out by 5, so we had to do Q in by 5, so that means we need to do Q out by 5 also. Right?
Is it because we're trying to find the work net at 5?
Because we're trying to find from the algebra, because we need it here, not at 5, but per unit mass flow rate of 5, right? Because to make this equation right here, where we're dividing by 5, so if we can't, to make this right, if we were to cancel mass flow rate 5s out, we would get the power here, right? So that means that's work net out per unit mass flow rate 5. To get work net out per unit mass flow rate 5 means we set out the power net out and divide. We did it 2 different ways. We did it with the pump and the turbine, we had to divide by 5, and we did it with heat in and heat out, we had to divide it by 5. So to make the algebra correct, everything has to be divided by mass flow rate 5. Okay, does that make sense?
Kind of, I guess, because the mass flow rate 5 is our whole like mass flow rate. Is that why?
It's the whole one, and because we're using it, we're going to solve for mass flow rate 5 right here. Let's do green, right? Or here, and we know this. That means we need to get this, okay? That work net out is per unit mass flow rate 5. So we have to get work net out per unit mass flow rate 5, so that means everything else has to be per mass flow rate 5.
I got you. I didn't realize we were solving for mass flow rate 5.
Yeah. So we're looking for, we have this, the given. So this was our given right here. When we need a mass flow rate, when we're solving for a mass flow rate, we need to have something that scales that mass flow rate, and they give us the power of the net power output of the cycle. All right. So that's, say, we said, oh, it's a 400 megawatt power plant. Okay, so what's the mass flow rate if we had this set up for the power plant? Okay. All right, so that means we got to divide by mass flow rate 5, and that's the trickiest thing about this problem, right? And that actually makes us kind of go down a rabbit hole of where we thought we were getting a lot less unknowns. We actually end up having to solve for a bunch more. All right, so we have an equation now for Q out. We have enthalpy at 1, we have enthalpy at 11, but we don't now have mass flow rate 11 divided by mass flow rate 5. Right? So that means we need to get mass flow rate 11 divided by 5. Okay. This is where we look where everything gets split. Okay, as I mentioned in the lecture. So we look at the turbine. Okay, so this is where that whole mass flow rate coming in at 5 and 8, which is the whole thing, which is like a 1, gets split where we have a fraction 9 coming off, fraction z, and then we have a fraction 1 minus y minus z at 11. And we can see that. Come on. Doing the conservation of mass on the turbine. All right, steady state. So we have mass rate 8 going in, 9 leaving, 10 leaving, 11 leaving. And if we now divide everything by mass flow rate 5, now we have, what's mass flow rate 8 divided by 5?
1.
1, right? And then 9 divided by 5 will be y. So that fraction that we're pulling off. And then 10 divided by 5 will be z. And then if we just move 11 divided by 5 over, that's what mass flow rate 11 divided by 5 is that we're looking for up here. Okay. So that means now we've went from one unknown, now we have 2 more. We have y and z. We got to get the fraction that's being pulled at the, so if we look at this again back in the schematic, we have the total 1, right? Right here. The fraction y comes off at 9, z comes off at 10, and the remainder, which is 1 minus y minus z, is there. So maybe 10% goes at y, 10% at z, so then we would be left with 80% at 11, or 80% of that mass flow rate 5 at 11, right? All right, so we need y and z, okay? So we'll start with y, okay? So let's start with y. We'll solve for y, but what do we got to do to get y? Let's go back to the schematic. So we need to find y here, right? What do you think, what component do you think we could use to get there? or what component would not have any, if we use the turbine, right, it has some work leaving the turbine, and we don't know the work leaving the turbine. So that adds another unknown, right? What component has no heat or work leaving its device, so that it minimizes the unknowns, but really just has mass flow rates and enthalpies that deals with Y? Let's see, state 9.
10.
10. Well,
10.
that's Z,
The closed feed water.
the closed feed water. So if we take our boundary around the closed feed water heater, right? There's no heat or work leaving the closed feed water heater. It just has 9, 4, 6, and 5 mass flow rates and their enthalpies. So the closed feed water heater, which is an open system, but it's not one inlet, one outlet, okay? So, but there's no heat or work, so we just end up with the mass flow rates carrying in or carrying out enthalpy. So we have mass flow rate 9 and its enthalpy being carried in. We have mass flow rate 6 and its enthalpy being carried out. And then we have 4, its enthalpy in, and 5 and its enthalpy out. Okay, so from conservation of mass flow rate 9 is connected to 6, and mass flow rate 4 is connected to 5. Okay, so if we go up to our schematic again, we can see that. So 4 is directly connected to 5. There's no mixing between 9 and 6. 9 and 6 is directly connected to 6. Okay. We could also follow it through and say, so 6 and 9 are connected, and 6 and 7 are the same mass flow rate also. Okay. Just like 4 to 5 is the same, which is equal to 8. We could also backtrack it. 4 is equal to 3 also. All right. So we get 9 is 6, but I also said that's equal to 7. 4, 5, we have 8, and we also have 3 in the same. Okay. Well, we only need for this part, we need these two because that's what's in our conservation of energy. Okay, so we have this. We need to do again, divide by mass flow rate 5. What's 9? Mass flow rate 9 divided by 5?
Y.
Yeah, so that's Y. And 4 divided by 5?
One.
Yeah, just 1. And we already grabbed all our enthalpies. So then the only unknown in this COE is Y, right? So you can rearrange and solve and get that. We are pulling 0.005, right? 5.4%, All right, this is being pulled and extracted in the first extraction stream. So if we follow back up our problem, we have Y. So then to close out our problem, we need Z, okay? How do you think we get Z?
The open feed water heater.
Yep, so the same idea, there's no heater work crossing our boundary and only mass flow rates and then their enthalpies for the open feed water heater, okay? So we have 10, 2, and 7 going in and 3 going out, right? All right, so we have 10 and its enthalpy plus 2 and its enthalpy plus 7 and its enthalpy going in, and then we have leaving 3 in its enthalpy. In this case, it's open feed water heater, so none of the things are connected independently. They're all just mixed together, okay? So we'll just divide from here by 5, mass flow rate 5. All right, so 10 divided by 5 is what? Z. What's 2 divided by 5?
One.
2 divided by 5 is go up to our schematic. We have mass flow rate at 2, which is the same as 1, which is the same as 11. So it's this 1 minus Y minus Z. Because we can't go forward because this is where it all mixes together, right? It's the same as 1, which is 11, which means it's 1 minus Z. Okay. 1 minus Y minus Z. 7 divided by 5? Y, yeah. And then 3 divided by 5.
1.
Yeah, it's just 1. Okay, so now we go through, we have all our enthalpies. We have Y. So the only unknown in here is Z. So we can rearrange and just get Z by itself. So that means we get Z. .1694, so that means there's 16.94% of mass flow rate 5 being extracted at the second extraction state. And now we go back up, see what we got. So now we have Z. So we have mass flow rate 11 divided by 5, so we could solve for it directly, or we can put it into our heat out. Okay, so now we can solve for heat out, since we have 1 minus Y minus Z is mass flow rate 11 minus 5. All right, we have the enthalpies, Y and Z. So we get Q out. 1549 kilojoules per kilogram. We work our way back up of what the heck we were solving, right? Now we have Q out, so we can get work net out per mass flow rate 5. We get 1278 kilojoules per kilogram. Now we have this, so we can just use our equation here now to solve for mass flow rate 5, because we have work net out and we have power net out. We have 313 kilograms per second. Okay, and then we could solve for the actual mass at those extracted locations, and a percentage of that, right? Any questions so far? All right, B is thermal efficiency. Okay. All right, thermal efficiency, desired output is work net out, record inputs Q in. We could easily solve for a rate of heat transfer in now, because we have the mass flow rate. So we could solve this way, okay, and just take mass flow rate 5 and multiply it times Q in, okay, and then get the rate of heat transfer in. Okay, we could go that route. We could also go the route where we divide by mass flow rate 5, okay, and I'm going to just show that part again. All right, so what we see here again is work net out divided by mass flow rate 5 and Q in divided by mass flow rate 5, and that allows us to make this equation here equal to the one above it, right? So when we do work net out times mass flow rate 5 and Q in times mass flow rate 5, we can cancel now the mass flow rate 5s, because the power net out and the rate of heat transfer are both divided by mass flow rate 5. So that cancels our mass flow rate 5. So we have the per unit mass version, okay? But it's again per mass flow rate at 5. We have both of these, so we could go this route solving the problem. You can also go the route of plugging in your Q in minus Q out. Again, this is all per mass flow rate 5. Or you could do the you can also do the turbine minus pump 1 minus pump 2. These are also per unit mass flow rate 5. Okay, so even if you went the turbine pump 1, pump 2, you're still going to end up having to get Y and Z, because there's different mass flow rates going through those pumps. Okay, the pumps are, pump 1 has y minus 1 minus y minus z going through it. Pump 2 has the total. So to get the pump 1, you're going to have to get 1 minus y minus z. So you have to get y and z in again there. So either route, you still got to get the fractions. Okay. So depending upon which version you go ahead and solve, right, we could have done this one, right? We could have done, we can do this one, and we can do this one, because we have all these, we have Q out and Q in. For this one, we would just need to solve for the rate of heat transfer. Okay. But if we do that, we go beep, 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 put it in our calculator. You get 0.5452, or do 45.2%. Any questions?
Yeah, for the one that we basically used of like showing the division of mass flow rate 5, do you have to show that division first before you rewrite it, or could you have just gone straight to writing it the way that you did on the right-hand side?
Do you have, this one? No, you don't have to do this. The why I like to do this is this, I want you to see where you could just write it like this. You just have to recognize that this is all divided by mass flow rate 5, right? We kind of had until this moment realized that we just did it in previous problems because it didn't matter because it was always the same mass flow rate, right? But now it really does matter, right? So that's why I showed this, if that's what you're asking.
Yes.
Yeah, that's why I showed that step. Okay. All right. Any other questions? So it also goes to show you can always, if you have all your state information, right, and you know your devices, you can get a thermal efficiency. It doesn't matter. It doesn't depend upon the size of the system. Thermal efficiency. It doesn't matter if it's a 400 megawatt system or a 1 megawatt system, because we have states 1 through 11, and the devices that they are, we have fixed states. If we have fixed states, then we have the thermal efficiency. Okay, that sets it up. That tells us the ratio of areas, which is heat in and work net out. Okay. Any questions?